study a specific type of motion, which is called the uniformly accelerated motion. Because the importance of this motion, so we will study this motion, since there are many and multiple examples in life where the object moves with constant acceleration. So, uniformly accelerated motion. We already studied the uniform motion, as I said before. Uniform motion is when the object moves at constant velocity, velocity constant. And in this type of motion, as I said, x as a function of time will vary like this, or will change like that. And v as a function of time will be constant. This is a uniform motion. So when you need to graph those two types of motion, it looks like that. Today, we will study uniformly accelerated motion. Which is when the acceleration is constant. And in order to study that motion, which today in the lab we will work pretty much this, or we will see this motion and how the sensor record the motion with the time. A constant, so we want to derive three important equations here. How? V change with the time. How x change with the time, and how, which is this. So we want to see the type of graph that will give that motion. Besides that, if I connect these two equations using substitution method or elimination, I can find what will be velocity as a function of position. These three equations are very important. It's good to know that for this type of motion, if the acceleration is, if the velocity is constant, so I derive that equation since I can derive from calculus. Let's derive the number one. These are called the big three for uniformly accelerated motion because they will be used very frequently in physics. One, v as a function of time. I will derive from this point A is dv over dt. This equation. Since A is dv over dt, in order to find v, I need to solve this differential equation, which I did before. And in order to solve for this, I need to go from VO to V final, from 0 to t. Same thing that I did before. Now the acceleration is constant when the argument or the integrand is a constant. What can you do to the integrand or to that value? You can take it outside. So we get V minus VO equal, I take out, and what will be the integral of dt? The t, right? From 0 to t will be t. So what will be my first equation? I move VO to this side, and I get VO plus AT. This is the big one. You can see that formula in your formula. Okay, so what is telling me this equation? if I want to graph v as a function of time, like I did here, now you can see that v changed with the time. How? What type of relationship between v and t? Linear. And linear, how looks a linear function? And what is this? At 0 time, how can I call that point, which is the y-intersecting math? If this is my equation, which is linear, on my equation, v is the function, y. VO is the y-intersect, which is the initial velocity. What is A? The slope, m, which is what I said here. The slope of that line, in that case it's a line, is the instantaneous value, or the average value. They are the same in this case, because it's a line. That's the slope. And t is the abscissa. So this is the graph. Anytime you have a motion, a constant acceleration, and I ask how it looks the graph, v versus t, very important for the labs, very important for our labs. V as a function of time, and then if you know that the motion is at constant acceleration, a straight line. If it's accelerating positively, the slope will be a positive slope. If it's accelerating negatively, how will it look like the graph v versus t? Instead of like this, with a negative slope, which you know that from math. Got it? So if the object is decelerating, negative acceleration, it will look like this. From here to here. If it starts with positive velocity. Got it? This is the v versus t graph. This is the relationship of motion of constant acceleration. Number one. This is big number one. How v changes with the time. Second. The second equation is how x changes with the time. Of course, if I want to solve for x, I need to go to this relationship. So this, dx over dt. So v is dx over dt. If I want to solve for x, I need to get dx equal v dt. And I need to solve for the differential equation. Integral, integral. From xo to x final. From 0 to t. What is the integral of dx? X. From xo to x equal to what? V is not constant. What is v as a function of time? V is not constant. We already proved that V is not constant. That changed like this, right? So what is V as a function of time? That's what we get before, VO plus AT. We just have to insert this here. If you insert that there, you get that the integral from 0 to t of VO plus A t dt. And now we solve this integral. So will be x minus xo equal. What is the integral of VO, which is constant? VOT. Plus, what is the integral of AT? Over 2, 1/2 AT squared. What will be x? You remember in the previous example that when I get a quadratic function, right? In the previous two examples before, when I give the quadratic function and we get the second derivative, we got that the acceleration was constant at all times. You remember that? Which we get, I think, -6. Yes. Right? Was because was quadratic. Every time that you have position versus time quadratic, you know that the acceleration will be constant. or if b as a function of time linear, you know that the acceleration will be constant, which is, this is the case. If the acceleration is positive, how will look this graph? So if it's positive, will be x versus t, will be a parabola like this if we start from this position. If we start from this position, will be like this. But if the acceleration is negative, how will look the graph x versus t? Concave downward. A versus t. Because this value, which is a in the quadratic function, a, you remember a, b, and c in the quadratic formula, right? This is a in the quadratic formula with respect to the time, not with respect to x. But this is the a capital in the function ax squared plus bx plus c. So that is this. So if it can start from here or can start from here, whatever, but will be a negative acceleration. So will be, instead of like this, will be like this. Maybe like this, or maybe like this, from where we start. Okay? So that will be a negative acceleration. Any question on deriving these three equations? How to deal with this equation? Once you know that we derive, and this is a quadratic, this equation, you need to know the graph, the type of graph for this motion, and for this motion. X, this. Now, to find the third equation, how we change with respect to x, we need to combine these two equations. This, if I combine this and with this, so I can find the time here, right? And I can replace the time here. So, for instance, the third equation, if we have that v, we can go to here also. Because we know that in this type of motion is linear, the average, and only for this motion, the average velocity is VO plus V divided by 2. Only for this type of motion you can do that, because it's a constant rate. You can add the two velocity and divide it by 2, the average velocity. So, but anyway, let's get if I go and I said that V average is VO plus V divided by 2, and that is delta x over delta t, x minus xo divided by t. This is this. V average delta x or delta r over delta t. But V average is the addition of both. And on the other side, I have that the acceleration is V minus VO divided by t, which is this equivalent to this. Replacing time here, so I can get time, and time is equal to V minus VO divided by A. So if I replace the time here, I get that VO plus V divided by 2 will be x minus xo divided by V minus VO divided by A, but I can multiply the A here. Instead of on the denominator, I can move to the numerator. And now, if I cross multiply, this is the difference of square. VO plus V times V minus VO is V squared minus VO squared, which is A plus B times A minus B, which is A squared minus B squared. Equal, I multiply by 2 here, and I get 2A delta x. So what will be V squared? VO squared plus 2A delta x. This is my third equation. How V change with the time.